Hi-oh, here we are again. This time we're talking about interference and how waves behave when they come across one another. Basically, interference is when you have two or more waves that overlap. Remember, waves are nothing more than the carrying of energy. So it's perfectly okay to do that. Watch as these two waves coming at each other overlap. They get much, much bigger, don't they? They add together. This can happen not only with the adding, in which we call that constructive interference, but you can also have them subtract out, and the amplitude is therefore decreased, and we say that they are out of phase, or there is destructive interference. So notice what happens as these come by each other. All right, we get a higher amplitude. So maybe these two waves, remember, measure amplitude from the midpoint here. So we get something that's twice as high. Here they've canceled each other out. For every bit that this one is up, that one is down. These are extreme situations of that. Again, the key words to know: destructive and constructive interference, in phase and out of phase, whether it increases or decreases. So how would you add these? How would you know what the resulting wave is? So I've drawn two waves ahead of time. One is a crest and the other is a trough. The zero line represents the equilibrium point. How would we put those together? Well, I would draw a grid like I did, and I'd say, okay, this one goes up one, and one over it goes down a half. So the net is up 1/2. The next one, this is up 2, this is down 1. So net up 1. And you would just keep going. Up 3, down 2.5. So up 3 but down 2.5 would mean we'd be right here. And so you can see what the resulting wave is starting to look like. When you have multiple wave sources and you can see them, we tend to get these interference patterns. We get these spokes right here, which are areas of destructive interference, and we get things that aren't spokes, which are constructive interference. So imagine, if you will, these two waves, right? Each one of these sources is creating a wave, and when they interfere, you get areas that are completely canceled out and areas that are reinforced. What about waves when they hit objects? Well, anyone knows that a wave can bounce off something. You look into a mirror and the wave bounces off. And of course we call that a reflection wave. And we know that waves can go through things. For example, light goes through a window. But what you may not have realized is what happens if the surface is not rigid. For example, this one down here. The wave reflects back the same exact way that it came in. What we're really interested in is this top one up here, that when the wave strikes a rigid surface, you get an opposite wave. So here it's coming in crest up, it leaves trough down. The reason why that was important is so that we can discuss standing waves, because that's exactly what's happening. A wave is coming in and then it reflects, and there will be points where there is destructive interference, and there's points that are constructively interfered, and you get a really neat looking pattern because of it. The parts of this pattern are nodes, antinodes, segments, and the fundamental frequency. We're not going to focus too much on sound and fundamental frequencies, only enough to know that they exist. First off, you've probably done this with a jump rope, right? You and a friend, you're standing and you're holding on to a jump rope, and you make it go up and down. It turns out the place where you're holding on to really doesn't move much, and in fact, in a perfect system, it wouldn't move at all. We would call that a node. And nodes is where there's destructive interference. The other parts that go up and down, the rope is sometimes down here, or it's up here. Those are called antinodes. And that's the maximum movement, or constructive. Each one of these segments, there's the word segments, is from node to node. So in this top one, there's one segment, the middle one, there's two segments, and so forth. That top one happens to represent the fundamental frequency. If this was a sound, this would be the lowest possible frequency in that standing wave. So the second one would be 2 times the fundamental frequency, the next one 3 times. Take a moment and see if you can fill in the table. So pause the video now and then restart it when you're done and check out the answers. And there's your answers. See if you got them right. Waves, when they move, have some very interesting effects. Some of this is very noticeable when it comes to maybe being in a boat on water. If you are traveling, let's say in a boat, and you might not be traveling as fast as the waves that you're creating. I think you know, you've seen things bob up and down in water. They create waves around them. So you can see in the front part of this object, the waves have bunched together, and in the back part, the waves are a little farther apart. That's going to be a little interesting and a bit important later on. But if you're going the same speed, notice you're traveling on top of this wave. And if you're on a boat, you find your boat is traveling on top of this big front wave. Notice they're constructively interference. There's a lot of turbulence there. Right? Each one of these crests are on top of each other. But if you're going faster than the waves, there's absolutely no turbulence at all. You're leaving all that behind. You're in front of all those wave fronts. We've been using the idea of water. But what about a wave like sound? Well, here we have a high frequency in front, right? Lots of waves in a small area. And on the back side, very few waves in the same amount of area. So we'd say it's low frequency. And that would relate to a low pitch. And likewise, a high frequency to a high pitch. You've probably heard this with a car coming by, a plane, or a train, the different sounds. That's exactly what's happening. And we tend to call this the Doppler effect. The Doppler effect is that shift in the frequency due to the movement. Now, it could be the object making the noise moving, or you could zip by it. So in other words, the movement is all relative. But here, in this first one, nothing's moving. They're sitting there. Everyone hears the same thing. But in the bottom, those waves bunch together, so we hear a higher frequency. And on the other side, person A sees or hears a lower frequency. We can relate this to light as well. This would be things shifted towards the red, and this one would look more blue. Interestingly enough, when it comes to water, you've probably seen these little V-shaped waves, and we call that a bow wave. It's this two-dimensional wave when you're traveling faster than the wave that you're producing. But what's really cool is when you put it into 3 dimensions. It turns out you get a shock wave, and it's a cylindrical, a cone-shaped wave that happens. And you've broken the speed of sound. So the person in the plane, they don't hear much. They just have a little bit of vibration, but it's a very smooth flight because they're not coming in contact with their own sound. Now, you may have heard of this thing called a sonic boom, and that happens, of course, because all these wave fronts are constructively interfering. But the plane is in front of that, so they're not having any turbulence or interference at all. But if you're standing on the ground, you will. These guys over here, they'll hear it eventually. This guy already heard it, and if somebody's standing right here, they're in the process of hearing that loud boom.